All right. Welcome everybody to this UGA speaker series. We're really excited to have Dan Sousa from San Diego State University here to talk to us. Thank you so much for coming in. I know it's pretty snowy here, so university is closed, but thank you so much for still attending. And I'll let Dan get started. We're going to have 15 minutes for questions at the end. So if you just want to put questions in the chat, we can answer them at the end. Hey, thank you.
All
Dan, you
right.
can get
I'll get started. Hi everyone, nice to meet you all. My name is Dan Souza. I am an associate professor at San Diego State University in the Department of Geography. And my expertise is in remote sensing, particularly of land rather than water, for instance, or atmosphere. And today I will be giving you a little bit of an overview of the kinds of things that we can learn from remotely sensed observations. My hope with this is that it will be big picture, interesting, and very informal. So I will do my best to monitor the chat. I'm totally okay if people would like to just barge in and ask questions as I go, but I will try also to end early enough to be able to handle as many questions as people have. I tend to be not great at monitoring the chat in real time, but just unmute and yell at me if you'd like. So let's see if looks like my screen I think is sharing and my slide should have advanced for everyone. So if it didn't, let me know, but otherwise I will assume we're good. Um, so big picture overview of the talk. First, hi everyone, this is me. Um, I'll go through a little bit of kind of who I am and how I got here to be speaking to you today. Then most of the talk will be about kind of what is this thing that we call remote sensing? How does it fit into our understanding of the Earth and our understanding of things geospatial? And then I'll end and have some time for questions. So first, a little bit about me. Um, I like to kind of repose the problem because when I think about who I am, I honestly still have trouble answering that. That's what in the world of geophysics we would call an ill-posed problem. Uh, so instead, I'll do a trick that I do in my research a lot, which is I'll rephrase the problem to something that I think I probably can answer, which is instead of kind of like who I am, more of how I got here, because I kind of have a handle a little bit on that. That would be more of a well-posed problem. So I was born and raised in Northern California, youngest of five. For all of my childhood, pretty much through high school and early college, I did a lot of manual labor, mostly on construction sites, and then also for residential home repair. Um, but I was always kind of interested in space and rockets and all that stuff. And so I definitely was interested, but had a lot of life experience that was not directly purely academic. So if there's anyone in here that maybe is feeling a little bit out of place at like a fancy university, I can relate to that. Um, if you stick with it, you can make it. So after high school, went to college at University of California in Davis, right around where I grew up. Our mascot is the cow, or the Aggies, and we it was a good place to go to school, honestly, because by the time I graduated from high school, I was not really ready to be totally independent from my parents, and it was good to be close. Um, so I could have a lot of support from my mom and my dad. But by the time I graduated from college, I was ready to leave. I Even by the end, I wasn't really sure what I wanted to study. I knew I liked science. Again, I kind of liked aeronautical space things. But I have always had and continue to have, as will probably be apparent with my research, a hard time making up my mind on just one thing to learn. So I like physics and I like geology and I like chemistry. And I kind of just took a bunch of science classes and turns out at UC Davis, if you do that, at the end, they can lump it all into a major, which they called natural sciences. So that was not my major until the very end, but it all worked out okay. So then as I said, I was kind of ready to leave. So I got about as far away as I could go and went to New York. When got my master's in climate and society at Columbia University. Completely different from where I grew up. I grew up rural. This is Manhattan, hyper urban. Whole different university culture, whole different set of students. Much more kind of on the applied policy side of things, because at the time I was very interested in kind of climate change policy, and ways to make an impact in the world that way. So from there, I did one quick internship with NASA through the Develop program. That's me, young and dumb. Uh, and the Develop program still exists, is still going strong, is always looking for applicants if you're interested in this kind of thing. Happy to chat with folks about what that's like. Um, and that was basically a summer. And then after that, I went back to the East Coast to Washington, D.C., and was a NOAA Knaus fellow, working on environmental policy for a congressman, uh, for a year, which was a fascinating experience. It was what I thought I wanted to do after my master's. And about a month in, realized it was absolutely not what I wanted to do with the rest of my life. There are some things that I'm pretty good at, and there are a lot of things that I am terrible at. And it turns out being a congressional aide is one of the things that I am really bad at and don't really enjoy. So it was a very valuable year-long experience. I realized kind of policy is not for me personally, and I went back to science. I had a master's class that was about remote sensing. It was interesting, but at the time it was kind of a passing interest. But I remember the professor contacted him and said, like, "Are you have any research jobs?" And he said, "Yeah, well, we're getting ready to go to Bangladesh." And so I said, "Well, can I come with?" And he said, "Sure, we'll pay you." So that led to working for him as a research assistant, which then became a PhD. And the main appeal for me there was I was interested in traveling to interesting spots, and learning how to apply my knowledge of the world in a little bit more of a rigorous, systematic, mathematical way. Led to some interesting adventures, which I'll cover a little bit later in the talk. And was really how I got started on what is now my career. After that, did a postdoc in Santa Barbara at a ranch, studying some interesting ecology problems. And then another one at JPL, which was another year of interesting exposure to kind of the real hardcore NASA science and engineering side of things. That was mid-COVID. So I was required to move to the area by HR, and was subsequently never actually allowed to go onto base. So I went in, I relocated my whole life, moved there and went in to pick up my badge the first day, and then was not allowed in until I returned my badge on the last day. So that was one of those life experiences where you grow. And then after that, got my job here, where I have been for now about 4.5 years. So, where I am now is in the geography department at San Diego State. This is our website. I'll just, because I am required to by my department chair, put in a little plug for those of you who are thinking about graduate school. We have master's and PhD level programs. Our master's is usually about 2 years. We have MA and MS options. And kind of core to our master's, which is these days getting increasingly rare, is it is really a research thesis master's. So it's not primarily coursework. There are classes that you take, but the core of it is independent thesis oriented research. Um, our PhD program is actually a joint program with UC Santa Barbara. Um, and it's a unique program in that students spend year one physically with us here in San Diego. Year two, they relocate and live and go to classes at UCSB, which, for those of you unfamiliar with the area, is about a 5 hour drive, depending on how long it takes to get through Los Angeles. And then for years three and afterward, they relocate back here. So it's a really cool program for the right student who is interested and willing to relocate a couple times, which of course is a little bit displacing, but gives you access to the whole faculty at two universities, which is pretty unique and can be a very enriching experience for the right student. So as of right now, it's unfortunately just a little bit too late to apply for this year. Our admissions committees are actually meeting next week to evaluate all the applications. Offers will start going out probably in March. Uh, but if anyone is interested, usually applications are due kind of in the December, January range. So we're always looking for uh, interested and capable folks for next year. We have faculty that span a pretty wide range of disciplines. Obviously, I work in the field of remote sensing. We have some really world-class hydrologists and kind of ecologists or biogeographers, as well as folks interested in really hardcore geospatial modeling and geocomputation, as well as a robust contingent of human geographers. If you're interested in any of this, ask anytime. And I will repeat throughout. Email is the best way to get a hold of me. I'm a little behind on it these days, but I do strive to catch up. And feel free to get a hold of me after the talk um, if you have more specific questions. Okay, so that's my spiel. In the about half an hour I have left, I will give you a little bit of an overview of this whole remote sensing thing. So when I'm thinking about this to an audience like this, I like to start kind of big picture, and a good place to go for that can be the National Academy of Science. They're really good at taking holistic evaluations of entire fields and summarizing concisely what the big outstanding questions are that we as a community are interested in. And I pulled some of these out of a report, which is linked on the bottom. I'd be happy to share this PowerPoint if anyone wants to follow the links after the talk. Um, and I've highlighted some questions, things like preserving biological diversity, understanding changing physical environment, sustainable agriculture, coupled human environmental systems, human health, and urbanization generally. And what I hopefully will give you a flavor for is that one of the cool things about remote sensing, one of the things that has attracted me to the field from the beginning, is that it really has the ability to give useful information into a really wide range of, and I would argue, every single one of these big picture questions. For those of you who are coming from the NASA worldview, it can be useful to also understand that various groups of people group concepts in different ways. And many of those National Academy questions can also be rephrased in a little bit more, say, specific, observable um, phenomena, which is what NASA often likes to think about, things related to ecosystems, biogeochemical cycles, climate, and Earth surface and the interior. And so, big picture, what are we doing when we're analyzing remotely sensed measurements? Well, usually we're working with imagery. And when we have an image that implies we have basically a rectangular grid or array of measurements, and those measurements are usually called pixels. And you, believe it or not, if we were in person, I would say raise your hand if you have any experience with remote sensing, and not very many people would. And I would say, aha, actually, you all do, because you have eyes. And when you use your eyes, for instance, right now, to interact with the world, you are measuring a field of light and using the color and the spatial uh, position and orientation of that light to break the world into objects and make inferences about the composition of those objects and how those objects might act. So we all have mobile phones, they have cameras. This is my dog, and we like to take pictures of our dogs. This picture of my dog, Nell, is a remote sensing observation. And it turns out mathematically and computationally there's not that much difference between the photos that you upload to your Insta and a hyperspectral science grade image that NASA would collect from their Avarice instrument. The key in taking the information from images that you're used to working with and using them scientifically is represented by this on the right, which is lab studies and mathematical understanding that links those values of how bright various colors are to physical understanding of what is happening on the surface of the Earth. And if you're going to understand one thing about remotely sensed observations about the Earth's surface, that, for instance, you might use in geospatial analysis, you need to understand that the core difference between basically all of the images you're used to collecting and looking at from your phone and the images you're working with that are remotely sensed of the Earth's surface is in the relationship of the resolution of the image to the scale of the objects. So you are used to looking at images where you have many, many, many observations, measurements, pixels within one object. So I know that this is my dog because there are lots of observations that are at the location of her eyes and her snout and her ears, and she's on the couch. But the images that you're working with when you're looking at a satellite or almost even all airborne images are like these on the right, where it's blurrier and blurrier and blurrier, and you actually very frequently have more than one object within a pixel. And there's a fundamental mathematical change in how you think about the information of the image when you have more than one pixel per object than when you have more than one object per pixel. And another sort of implication and representation of this is very often people will use uh, satellite images to make maps, and they will classify every pixel in the map as a material or a label. They'll say, this is a farm, and this is a city, and this is a lake. And when you're doing that, you're making a statement that that whole area represented in that square, which is covered by the pixel, is made up of one and only one category of thing. But we all know from walking around and interacting with the world that the actual trees and cars and cows that are around us are not perfectly square and they do not align perfectly with the edges of the totally arbitrary grid of our imaging system. And so a visual like this can be useful to keep in the back of your mind when working with remotely sensed imagery, to have an intuition for the limitations of labeling every pixel as one and only one thing. So now I will quickly spin through each of these big picture questions, starting with biological diversity. So another really cool thing that we're really just starting to get a lot of observations from now is a tool called imaging spectroscopy or hyperspectral imagery. So the images that you're used to working with are what we would call true color images. So they measure light at visible wavelengths. Now, it turns out that there's light at all these other wavelengths as well. And the visible wavelengths are interesting, but are totally incomplete in representing the color of an object. So the science of understanding the relationship between the interaction of light of an object and its composition is called reflectance spectroscopy. And if we were in a class, I would ask everyone to raise their hand if they have ever had an organic chemistry class or remember from back in the day when they may have once learned about principles of infrared spectroscopy. And this is where the world is made out of molecules, and the molecules have atoms, and the atoms are connected by covalent bonds, and the specific properties of every covalent bond pair. You have a one, maybe it's an oxygen to a hydrogen, and those have charges, and there's a known length, and the charges and masses of those will set stretching and bending modes of variability of how those atoms move. Those modes of variability result in absorbing light at particular wavelengths, and that produces, for some materials, characteristic infrared absorption spectra, which is how organic chemists determine the composition of all kinds of molecules. So, what I think is really cool is that hyperspectral imagery or imaging spectroscopy is applying those same principles that are like fundamental quantum mechanics, but instead of studying a really pure, well understood compound in a lab, it's applying it at a scale of a whole landscape. And it's contending with all of the spatial complexity and heterogeneity and mess that we have that represents the real surface of the earth. And it turns out that for plants in particular, all the compounds in all the plants uh, can have characteristic absorptions that represent chlorophyll pigments, xanthophyll, phycocyanin, cellulose, lignin, all that stuff. And when we have a hyperspectral measurement as opposed to a just RGB visible wavelength measurement, instead of only measuring these wavelengths of light that correspond to what our eyes can see, we also measure all of this in the infrared and shortwave infrared, which has a lot of really useful information in it, um, and allows us to make maps of the spatial variations of those compounds, which then in a context like the mangroves in Bangladesh that I was studying can let you make maps of spatial variability, for instance, in species of trees, which then helps us understand the status and trends in biological diversity. So if all that made sense, that's kind of the core physical principles behind hyperspectral imaging. And we can apply that to all kinds of stuff. And if I have time toward the end, I will show you a hyper recent example of that if I can move quickly enough. So moving on to changes in the physical environment. Um, I this is a question I always say, who here has any emotional attachment to the element tungsten? Often people say, I don't know what you're talking about. It turns out this is just one of many really important minerals or materials that goes into all sorts of construction manufacturing. And it doesn't just magically appear. It comes from mines. And it turns out that often these mines are in places that don't necessarily have the same environmental health standards as we have in the United States. And as of today, the world's largest open pit tungsten mine is in northern Vietnam. It's an area we're studying. We have samples from before and now after the construction of this gigantic open pit mine, obviously with huge implications for environmental and human health. This is a case where we can only really image it well recently because of advances in construction of instruments and lowering the cost of launch to space from things like SpaceX, um, allowing for large constellations of low cost but high spatial resolution imaging satellites. Um, these are not hyperspectral, but they provide very frequent, very spatially high resolution images, which allows us to study phenomena like this. Also, there's a story with wetlands here, which I think I will probably skip for the sake of time. The short version of which is we can evaluate year on year changes in hydrological status in a wetland across an international border here, US, Mexico, um, due to the lining of a canal that previously was basically just a hole in the ground and was lined with concrete in the early to mid 2000s. We have historical imagery that precedes the lining, allowing us to study year on year changes in subsurface flow and recharge to these unique wetlands. Um, Similarly, in the area just north of there is one of the most productive agricultural areas for a specific set of specialty crops in the world, and also gets really, really hot because it's in the middle of the Sonoran Desert. Obviously, there are human health implications for those working in the fields. And the same satellite that allows us to study the changes in the wetlands allows us to study spatial and temporal variations in heat stress, both in the afternoon and in the middle of the night, which can help understand health implications and hopefully make the problem less bad. So, moving on to human environment systems, another case of something I studied in grad school. Here, we're moving to the country of Oman in the Arabian Peninsula. You might think Arabia, hot, dry, no water. And you might be surprised if I told you that right where that arrow is, there is one of the only non-tropical cloud forests on Earth. And you might ask why, and the answer is that it has to do with the existence of something called the Arabian monsoon. So, for those of you who learn about monsoons, giant area of Earth gets really, really hot in the summer. Here we are talking about the Tibetan Plateau. Um, Creates an atmospheric low, warm, moist air runs on land and rains a lot. Then in the winter, it gets cold and that reverses. And this area here is just far enough close to the western edge of the Himalayas that causes that phenomenon that warm, wet air from the Arabian Sea flows over the land, creates conditions that basically everywhere else in the region are just miserably hot and humid in the summer. But just in this one spot, there is enough local topographic relief that the water hits the mountains and creates horizontal rain, which gives just enough water to the landscape where it looks in the summer like this lower right area. It's actually a regional tourism hotspot because of it's kind of the only place in the area where this phenomenon happens using the same approaches we were using in the Imperial Valley. We can make a map of spatial variability of the what's called vegetation phenology, or when the vegetation gets green seasonally, how green it gets, and how long it stays green. And then we can link multi-year changes in that to multi-year changes in the monsoon. Moving on quickly to health. So same set of observations, also in California here, can be used to make maps of things like mosquito-borne disease risk. Here we're looking at West Nile virus, which is a major issue here in California, um, particularly in agricultural regions. And one of the cool new things we have now is an instrument called EcoStress, which is a thermal imager on the space station. It turns out that mosquito behavior is highly temperature dependent. If it's too hot, they hide. If it's too cold, they are too cold and can't move. And there's peak, and that peak intersects with the hours they like to move around, which are usually first thing in the morning and late in the evening. And the unique capability of eco stress is because it's on the space station, and the orbit of the space station precesses, or the time of overpass locally changes from 9 a.m., 11 a.m., 1 p.m., 3 p.m. We can get high resolution thermal imaging of a landscape at various stages of the heating and cooling cycle of the day, allowing us to improve our understanding of vector-borne disease risk. Lastly, um, urbanization, where people live. Uh, Everything we have been looking so far has been images of the Earth during the day, but it turns out the Earth has color at night as well. This kind of requires a special set of instruments because just like taking a picture of the moon is really hard when you are hiking, there's so little light that the cameras need to be recalibrated to have longer exposure times and all that stuff. But we have more and more of these now, and at continental scales, provide us really interesting maps of the sort of spatial networks of lit infrastructure. Globally, people use these to do things like refine spatial disaggregations of census measurements. So, coming up with more accurate understanding of spatially where people live. And then one thing that we did that was interesting was in COVID, if you overlay that spatial network with the history of COVID transmission, you can observe the historical progression of the disease as it migrates through the interconnected lit network of where people live, which can be a lot more useful, for instance, than all the maps that were often used showing things just aggregated by county or other administrative unit. Um, Here's an example in Southern California. This is Los Angeles and San Diego of uh, showing human population from census just on the basis of administrative unit. And then this is it aggregated on the basis of night lights. And obviously, there is an improvement, particularly in rural areas like up in the valley here, which can be useful for those interested in understanding a little bit more granular detail where people live. Lastly, and I'll close on this, um, kind of hyper recently, people have been severely impacted out here, as you probably heard about the recent wildfires in Los Angeles. $30 billion at least of damages, people's lives totally upset. Lots of my colleagues at JPL actually directly impacted. The house I lived in while I worked there is now completely destroyed. And so remote sensing things we're working on right now are using high resolution aerial imagery to make maps of building level impact of the fire. Obviously, these are not perfect and are not as accurate as they would be if you were to go there on the ground, but can be automated at scale very quickly, which can be useful for immediate response. And then back to that hyperspectral stuff, we have hyperspectral imagery of lots of these areas before and after. And you can see examples of that spectroscopic change of the same area. Here in the upper left, we're looking at chaparral. Uh, it's got chlorophyll, it's got leaf water before, and then after. This is a spectrum of ash. Um, Another example, here we are in a community park before the fires, well-watered grass. Afterwards, surprisingly, still grass, but these absorptions here, which those among you with infrared spectroscopy experience may recognize as being associated with liquid water, are now completely gone, indicating, as expected, a loss of leaf water in the grass. Um, other instances of roofs here, looking at clay, um, completely destroyed, as well as the unique spectral signature of some plastics. All of this is kind of the next generation. Starting this field now would be really good to learn about because they're just getting more and more of these observations globally. And I always like to end on a note that this is really a good time to be starting to learn this subject because all of the world chaos notwithstanding, it is in it's an industry in the phase of pretty rapid growth. So with that, I will close on the note that take everything I just said with a grain of salt because even Einstein didn't know what he was doing. And I will take some questions. And I see there's some chats. Oh, there's links. Thank you, all of you, from those nice links. That's great. And yeah, I'm happy to email these out, and the links are live in the PowerPoint. And anyone interested can work straight from the PowerPoint. Let's see. The Ames Research Center. Um, the first answer I always like to give is that develop is fundamentally an applied sciences program, which means that at its core is it's really important that it is driven by the needs of the end user. And so I don't know what your project, Nicholas, is all about, but I assume there's an end user that is the partner. And it's really important that the objective of the internship is well aligned with what that partner wants and would like to use. Um, uh, I found it to be a really great learning experience. But I also will note the program has changed a lot over the years. And when I did it, all of the experiences were in person at a NASA lab. And I know that since the program has expanded, and especially with COVID and everything, there are now lots of those options that are remote. And there are also nodes that have been established at universities or local agencies that are not NASA labs. And I honestly don't have a lot of experiences with that kind of a NASA develop internship. Um, when I did it, again, like more than a decade ago, a big part of the learning experience for me was being on a NASA lab, seeing all the cool hardware that they had, meeting in person the people that worked there. And I could imagine that being a substantially different experience if you were not in person or if you were not physically located at a lab. So it's the develop internship in particular is really project specific and is the students I've spoken with have had the entire range of experiences um, based largely on the project they're working on and the location that they're at. So, a lengthy answer, but hopefully generally addresses the question. What future sensor development am I most excited about? Well, I kind of came from the hyperspectral world originally. My original interests are all in kind of the underlying physics. So I'm currently a funded member of the EMIT science team. EMIT is a hyperspectral imager that's also on the space station. It's kind of a parallel instrument to the EcoStress one that I mentioned before, and is not really future. It is collecting measurements now. And I am really excited about that because it's the first global um, critical for hyperspectral is it's a high signal to noise. It's a really high quality measurement. And so for my entire career, there was this whole set of questions that were like, well, this is what we can do now with multispectral Landsat. And then once we get hyperspectral imagery, we'll be able to do all this other stuff. And the launch always gets put off and it's later and it's later. And now I'm excited because we're finally at the point where we are collecting that global scale hyperspectral high quality imagery and we can start working on those that whole new set of questions. So that's kind of my uh little bit of where I'm coming from. I'll also add one thing that I didn't show examples of, but we're really scaling up here, and is increasingly interesting to me is we're as the cost of UAVs has gotten lower, and as the cost of LiDAR instruments has gotten lower, we're collecting now in the field, kind of related to the wildfire work I mentioned, some really interesting, really high quality UAV LiDAR. For instance, before and after prescribed fires that we can then use as really accurate measures of uh, vegetation consumption, which can be linked to measurements on the ground of things like fire behavior, temperature, all that stuff to improve our predictive models. So that also is a side of things that I'm really interested in. Let's see. Oh, more on the developed stuff. Idaho State. Cool. That sounds good. Experience or knowledge of the Department of Defense. Yeah. So, I another internship that I didn't mention, but that I did during grad school was I worked for a couple summers at the U.S. Naval Research Lab, which is actually pretty close to you all. It's in Anacostia, Maryland, in the Washington DC area. It was a really interesting experience. And I actually almost worked there full time, but all my family's in California, and it's kind of an East Coast, West Coast life choice. But lots of really interesting work there. The stuff I was working on there was all about understanding what they call trafficability, so kind of load bearing capacity and ability to move around on in the coastal environment. So is the vehicle going to get stuck in the mud, that kind of stuff. And there's kind of a hyperspectral component to that, as well as all kinds of capability with ground and UAV based LiDAR. Yeah, really interesting work there. And increasing partnership with NASA and other federal federal agencies as well. As actually on a call yesterday where one of the kind of application areas that everybody's trying to get momentum toward is using um, the assets that already exist for National Guard in particular, but also other DoD assets for monitoring of active fires. Because there's all of this effort and money that has gone into hardware capabilities for really high quality airborne thermal imaging that could easily be repurposed to help out in an active fire situation. And really the limitation there is bureaucratic, agency to agency, different cultures, needs for security clearances for some things, and maybe they don't really need to be totally security clearanced. And that's kind of a would be a really low cost capability that we could do right now that really just would require interagency coordination. And if you're interested in kind of the remote sensing of wildfire stuff, another project I'm involved with is called the NASA Fire Sense program. And they're all about exactly that of how can we use existing or like very near term advances in remote sensing to improve our understanding of pre-active and post-fire landscapes as air quality issues from things like smoke. See. Any other questions? I'm happy to stick around a little bit after the hour if folks want to, or I'll leave it up to the hosts on how to handle that. You can also just shout them out if you're interested. And yeah, actually that last link there is great. And related to emit and particularly in the hyperspectral world, a major use case of hyperspectral imaging is to monitor methane. And it's such a major use case that there's a increasingly robust private sector presence there. And there's a lot of crossover of scientists from federal labs going to work in industry and all that. And they actually almost worked for one of those companies too. There's an element of monitoring leaks from, for instance, natural gas pipelines and infrastructure, which is something that hyperspectral imaging is quite good at, and is a major source of both just methane contamination in the atmosphere as well as, loss of revenue for hydrocarbon production and distribution companies. Um, and our ability to do that from space has increased dramatically in the last 5 years. And those interested in sort of private sector jobs, there's a lot out there for that right now. Things like Carbon Mapper, Planet now has hyperspectral capability. There's a company called Orbital Sidekick that is particularly just focused on the hydrocarbon production question. There's lots of private sector activity right now.
Well, thank you, Dr. Sousa, for speaking to all of our students, and thank you to everyone that attended. We will be posting this to our website and look out on our listserv and across our social medias for any future speaking events that we'll be hosting.
Thanks a lot for
Thank you.
having me. Nice to meet everyone.